Hi, everyone. Thank you for coming to my talk. I'll be talking about my paper, Optimal Nash Equilibria for Bandwidth Allocation. Okay, so what is bandwidth allocation? We'll assume there are n agents and m divisible goods. Each represents a link in a network. Each link has the same total available bandwidth. That's just the assumption we're going to make in the talk, but it can easily be extended to a more general case. And we're going to assume that each agent has a fixed path, and she wants to send data along that path. So this is a standard Kelly model. And you can see in this diagram here, there's a particular source, and there's a destination, and it has one particular path that it wants to send data on. We'll let xij denote the amount of bandwidth agent I has for link j, and the utility then will be the minimum bandwidth she gets over any of the links in her path. One question I get a lot is why not let agents choose their paths? Why are we saying each agent has to have a single path that's fixed in advance? Well, there are a few ways to answer this. The first is that it's not really how the internet actually works. Usually routing, as in choosing a path, and bandwidth allocation are separate problems. They're handled by separate procedures within the internet. Specifically, routing is usually handled by IP and bandwidth is handled by TCP. That said, that's certainly still an interesting model you could consider. It's just not the subject of this talk. Okay, so here's a simple market mechanism we could use for this problem. Give each agent $1 of fake money, put some price on each link, and we're going to charge you for a bundle of bandwidth according to those prices. Each agent purchases her favorite affordable bundle, and we get a market equilibrium. This is called competitive equilibrium from equal incomes, and is known to have a variety of nice properties. Well, in particular, it's going to maximize Nash welfare, the product of agent utilities. It also satisfies things like envy-freeness and other properties. One thing I want to point out is that this situation is different for quasi-linear utilities, which is the subject of a different one of my talks, also at WINE this year. And for quasi-linear utilities, these equilibria for linear pricing aren't going to maximize Nash welfare. They're going to maximize a different welfare function, and I will discuss that then. Essentially, the qualitative insights we're going to have are going to be similar, but the technical details differ based on whether each agent has fake money or has real money, which is the case in quasi-linear utilities. Okay, so for our purposes, equilibria maximize Nash welfare. There's a problem with this, though. How evil are you? Would you lie about your preferences to a poor PhD student just trying to compute a market equilibrium? And essentially, what I'm saying here is that agents might have an incentive to lie about their preferences. And if we're just trying to compute a market equilibrium, we can't necessarily count on them to actually tell us their true preferences. Okay, so to handle this, we're going to use a mechanism called trading post. And in trading post, what happens is each agent submits a bid for each good, kind of how much they want to pay. It's essentially they get to allocate their budget of fake money across the goods however they want. And you can see it's subject to that constraint where the sum of their bids cannot exceed their 1 unit of currency. So for each good, agent I gets an amount of bandwidth proportional to their bid as a fraction of the aggregate bid on that good. We can think of the aggregate bid, so the sum over all agents of the bids, as sort of the implicit price of good J. That's how much you need to bid in order to get 1 unit. Okay. And so there's a theorem from a different paper back in 2017 that basically says that in this bandwidth allocation setting, they use a slightly modified version of the trading post mechanism such that the Nash equilibria are all within epsilon of the competitive equilibrium from equal incomes. I'm kind of rephrasing the result in our terminology for this talk. That's essentially what it does. So that's pretty cool, and we know that the competitive equilibrium from equal incomes, or the what I'm calling the explicit pricing market equilibria, we know that those maximize Nash welfare, so everything is great. And one of the key properties that they use, which we're also going to use, is that in this bandwidth allocation setting, or the more general setting of WINE'20 utilities, agents are always going to purchase in a fixed proportion. So for bandwidth allocation, they always want to purchase the same amount of bandwidth for every link in their path. There's no point in buying more bandwidth for one link. So at this point, we could declare victory and just say, okay, great, we have a mechanism that is going to get within epsilon of the optimal Nash welfare, and it handles incentives. So where do we go from here? Well, my favorite family of welfare functions, which also is covered in one of my other talks at this conference. So a welfare function in general says how good each allocation is. And the CES welfare is defined as follows. So it takes a parameter rho, and the CES welfare of a given allocation is essentially the power mean of the agent's values. Okay, I'm going to discuss CES welfare a little more in depth in the other talk. So for this talk, I just want to say that this generalizes a lot of the well-known welfare functions. If we plug in rho equals 1, we get the sum of valuations. That's utilitarian welfare. If we take the limit as rho goes to 0, we get Nash welfare, the product. The limit to negative infinity gives you egalitarian welfare, or the minimum utility. Okay, CES stands for constant elasticity of substitution, by the way. So the question that we set out to address in this paper, and we're going to talk about in this talk, is can we design a mechanism, and it's going to be parameterized by rho, whose Nash equilibria will maximize CES welfare with respect to that same value of rho. And turns out the answer is yes. Maybe you guessed that already based on the title of the talk. And the caveat is it doesn't work for rho equals 1. And we'll see why that is. That's actually one of the main open questions that we leave is, can you do this for rho equals 1? Can you design a mechanism whose Nash equilibria maximize utilitarian welfare? Okay, so this is the plan we're going to follow for this talk. The first thing we need to do is have an explicit pricing scheme, by which I mean ignoring incentives, where you give explicit price for each good. An explicit pricing scheme that leads to market equilibrium maximizing CES welfare. Luckily, that's already done back in 2019. Okay, the second thing we have to do is remember that this type of scheme also has the same issue with strategic agents. The agents might misreport their preferences. Okay, cool, we just did that. We just remembered that. So the main thing we're going to talk about is we have to find a way to convert that explicit pricing scheme into an augmented trading post mechanism. There's going to be a fancier version of trading post that has the same basic idea as trading post, but is going to be generalized using this more sophisticated pricing scheme to handle all of CES welfare instead of just Nash welfare. Okay, so the concept of price curves is going to be important. Essentially, these are just nonlinear prices per good. Like we talked about, we know that linear prices will maximize Nash welfare. So instead, we can assign a price curve to each good, where each price curve is a non-decreasing continuous function. And the cost of a bundle is just going to be sum across goods of the price you pay for each good. Okay? And these price curves are anonymous, meaning that the cost only depends on the bundle you get. It doesn't depend on your identity or your preferences or anything like that. Okay, so price curve equilibrium just basically gives a price curve to each good, and then you want the demand to equal the supply, just like normal market equilibrium. The 2019 paper I mentioned, they show that for any rho between negative infinity and 1, not including 1, We can find price curves such that the market equilibria will maximize CES welfare. So that's the first step we needed, an explicit pricing scheme that will maximize CES welfare. To say this a little more formally, if you pick some row in that range, and you let Q1 through Qm be optimal Lagrange multipliers for a convex program for maximizing CES welfare, we can then define each price curve by Qj times x to the 1 minus rho. And you'll notice that if you plug in rho equals 1, that actually reduces to a constant, which is kind of weird. That's basically saying you're going to pay a constant price no matter how much you get. And that's an intuition for why the rho equals 1 case does not work. But if you take this pricing form, then the market equilibria will all maximize CES welfare. Okay, so with that in hand, let's talk about an augmented trading post mechanism. Okay, so as before, each agent is going to submit some bid on each good. And we have the same allocation rule where each agent gets awarded bandwidth in proportion to her bid as a fraction of the total bid. The key difference is that instead of that linear constraint, we're now going to have a non-linear constraint. And you can see that same 1 minus rho show up. And now we're still going to sum across goods, but your bid for each good is going to be raised to this 1 minus rho exponent. And that basically means you're going to be penalized for bidding too much on one good. So as rho gets smaller and smaller, then it's going to become harder and harder to buy a lot of a single good. So for rho equals 0, you're going to get that linear price. And then for rho equals 0, you have linear prices. For negative rho, it's going to get harder and harder to buy more. So it's going to incentivize everyone to buy a smaller amount. And for positive rho, you're going to have a concave price where it actually incentivizes people to buy more. Note that people are still going to buy in a fixed proportion. This is just going to sort of affect the overall allocations people end up with. Okay, and notation-wise, we'll denote this by ATP of rho, augmented trading post of rho. Okay. So the main theorem in this paper is that every Nash equilibrium of this mechanism is going to maximize CES welfare. And at least one Nash equilibrium is guaranteed to exist. We'll just give some intuition behind the proof. If we define the price curves as before, so Q1 through Qm are going to be the Lagrange multipliers from the convex program. For the purposes of this intuition, let's just assume that the Qj's are all equal to 1. So let Y be any equilibrium allocation. That's the market equilibrium, the explicit pricing equilibrium. We know that Y is going to maximize CES welfare. Imagine that each agent just bids exactly equal to what their allocation is going to be. We can claim that this is going to be a Nash equilibrium of our mechanism. The first thing is to show that the bids obey the constraint. So the aggregate bid that each person is placing, this sum over all the goods of Bij to the 1 minus rho, that's just equal to sum of Yij to the 1 minus rho. And that's equal to the cost of that bundle Yi under the explicit pricing F. We know that that's less than or equal to 1 because in order for it to be a market equilibrium, each agent has to obey their budget. Okay. If we have these bids, each agent is going to get the following allocation. Xij is equal to this fractional allocation we mentioned, which is going to be Yij divided by sum over k of Ykj. And we know that that bottom denominator is exactly the total supply of the good. And the total supply of the good we've assumed is 1. So this means that the allocation is exactly equal to Y. Great. So X is just the same as Y. X also maximizes CES welfare. Great. We didn't quite show that X is actually also a Nash equilibrium. It's a little trickier. And what if these QJs aren't equal to 1? So it turns out that scaling them doesn't really matter that much for the purposes of our trading post mechanism, that scaling will arise naturally out of the bids, but that takes a bit of work to show. And also, we were only showing that this is a Nash equilibrium. We also want to show that there are no other bad Nash equilibrium. So there's still a bit more work to do, but this hopefully gives you some intuition. To wrap up, we said that for any row between negative infinity and 1, not including 1, we give this mechanism ATP of rho, such that every Nash equilibrium maximizes CES welfare, and there exists at least one Nash equilibrium. On a qualitative level, simply allowing these nonlinear constraints made this mechanism a lot more powerful. And this is a theme in my other talk also, that if we take these cases where we're used to using linear constraints, linear prices, and we allow some nonlinearity, that can actually dramatically boost the power of these market mechanisms. For trading post specifically, it has this interesting property where it can simulate an explicit pricing market, in that you still get these bids, except the bids arise implicitly from strategic behavior, which allows it to handle strategic behavior in that way, specifically because the equilibrium is a Nash equilibrium. I do want to mention that this is specific to bandwidth allocation or Leontief utilities. In general, trading post equilibria will not match up with the explicit pricing equilibria. So that's why our result is limited to this class of utilities. But there's other work that investigates other classes of utilities. Again, I want to mention that the technical specifics here are different from in the quasi-linear utility model, which is the subject of my other talk. The qualitative insights are generally the same, in that allowing nonlinear prices can help a lot, can give you a lot more flexibility, and also allow you to maximize this whole family of CES welfare functions. Basically, you get to pick which value of rho you want, or pick what equality efficiency trade-off you want, and then you can choose the exponent for the pricing curves correspondingly. Okay, for future work, rho equals 1 we did not address. I mentioned why the current approach will not work for rho equals 1, but we don't have a counterexample. We did show that, in general, fully strategy-proof mechanisms are not going to work, either for rho equals 1 or for other CES welfare functions. You can find that in the paper. And also, like I mentioned, can you do something for other classes of utility functions? Trading post won't immediately work because when people don't buy in fixed proportions, the trading post Nash equilibrium won't match up with the market equilibrium, but maybe other mechanisms can still work for other classes of utility functions. And that's all I have. Thank you for coming to my virtual talk.